So we have studied about the strain energy yesterday, like when we try to pull a wire by certain amount, delta L, then the strain energy stored is equal to strain energy stored per unit volume is equal to half sigma stress into strain. Okay, the strain energy stored per unit volume, the strain energy stored per unit volume, okay, half stress into strain, that is the strain energy stored per unit volume. Remember, unit volume is very important here. Okay, so it came from the fact that work done is equal to integration 0 to L force into dl. This is the work done. Okay, so so you know what is force, like like your stress, Young's modulus, or your stress by strain is equal to Young's modulus, then F by A divided by small l by capital L is equal to Y. So you know how much is your F. Okay, so it is Y A small l by capital L. So A will go up, Y A small l by capital L. So by replacing this and by doing the integration, you will get half W is equal to half into Young's modulus into strain. So all these things, once you simplify, you will get stress into strain into A into L, capital. So
A into L is
A into L. Okay, so here, okay, not capital L. Here you are saying L. One is L, other is del L. Okay, this is your wire of length L. Okay, so you are trying to extend it. So your length is L and you are trying to extend it, you are putting some weight and you are trying to extend it by length, let's say delta L or PL. Sorry. You are trying to extend it by L, small l. Okay, so let me check. Actually, it is not small l, it is capital L.
Okay.
This is capital L. This is capital L. You are putting capital L here. Okay. So you are integrating dl from 0 to L. Like if this is the length, you are extending it by small l. This is capital L. So you are saying FDL 0 to L.
0 to L. Okay.
Then you are coming out using this equation, you are getting by integrating, and from this you are getting this.
Understood.
That is the strain energy. So we are trying to do some numerical yesterday. Okay, I have just put so this is just a recap of strain energy what we have done yesterday. Anyway, we have derived it, so no issues. That you understand that, I hope. There can be a numerical on this. Be careful that half stress into strain is strain energy stored in the wire. If you okay, so we were doing one numerical of, because you have studied now Young's modulus, rigidity modulus, we have studied about longitudinal strain and shear strain and all that. Okay, so a numerical will do a square lead slab of of side 50. Okay, it is square slab. Its side 50. The square has a side 50, but its depth is 10. So if you see from the top, its
It
depth
is
is
10,
10,
10.
but this is a square slab. Okay. Um, then CM is subjected to a shearing force
9 into 10 power.
Force on its narrow face, okay, of 9 into 10 to the power 4 Newton, okay. So the question is, the lower edge is riveted to the floor, okay, and this is riveted, it is fixed,
Yeah.
okay. How much will the upper edge get displaced? And the question is, what is the value of this? The question is, how
Understood.
much is the value of this? Okay. So, A square. Okay. So, how to find it? So, we are seeing that force is acting on the upper face. So, area is equal to 50 into 10 is equal to 500 cm square. Okay. So, cm square we know 500 into 10, 1 cm is 10 mm, right?
Yes.
10 mm whole square. So 500 into 100 mm square, okay? Equal 5 into 10 to the 4 mm square. So this is the area
Yes.
on which it is acting, okay? So this mm square also we can convert into meter square. So area is equal to 5 into 10 to the 4. Then mm we can write as minus 10 to the minus 3 meter.
Whole square.
Meter square. Okay. Then this is meter square. Okay. So this becomes 500 square. Clear?
Yes.
Because 10 to the 6,
Yes,
10 to
yes.
the minus 4. So this is the area, and we know the force. Okay. So
Yeah.
knowing the force and this we can find out the shear stress on this slab. So the shear stress. Okay, because the load is acting parallel, right?
Yeah.
So we can find out the shear stress. So how much is the shear stress? Is we write it as tau. Okay, others longitudinal stress we write as sigma. Shear stress we write as tau, which is nothing but F by A. So let it be let it be force. I know how much force I am applying. 9 into 10 to the 4 Newton, right? Newton
Yes.
divided by I
Area.
got in meter square.
That's meter square, no, not square.
No, 10 to the minus
Minus
3
6
meter
into 10
square.
power 4.
So it will become 500, na? Sorry, meter square, correct. So 500 meter square. 5 into 10 to the 2 meter square. Okay, so your stress become
10 power minus 2. 10 power minus 6, 10 power minus 6, 10 power
Oh,
4.
10 to the minus 2. Okay, correct. So 5 into 10 to the minus 2 meter square. Okay. So it become like when the 2 goes to the up, 9 by 5 into
10 power
10 to
6.
the power 6 Newton per meter square. Right. So it becomes 1.8. 9 by 5 is nothing but 1.8. Then it is megapascal. Right?
Yeah.
Pascal.
Yeah, 10 power.
Okay, this is all. So, okay, so we know we want to find out this.
X.
We want to find out this. So we know stress now. Okay. So another thing we know is tau by shear strain. Okay. Let us say shear strain is written as gamma. Okay. Shear strain is written as gamma. So again, we want to find out your del x, right? Del x is what you want to find out,
Yeah.
right? So you want to find out del x. your aim is to find out del x by how much it has got displaced. Okay. So you know tau by gamma is nothing but your shear modulus. See, we have Young's modulus y
Yes,
for longitudinal case.
Yeah, yeah.
We have shear modulus G for shear load.
Bulk modulus
Huh,
and B.
huh. So your gamma will become tau by G, right?
Yes.
Right. Then your gamma is nothing but your del x by L
L.
is equal to tau by G.
G.
L you know as 50.
T.
Okay.
0.5 meter.
So del x, that is 50 centimeter, right? Let us see how much it is. 50 centimeter, okay?
Yeah.
So it becomes 0.5 meter,
Yeah.
okay? 50 centimeter divided by 1000, no,
100.
divided by 100. 1 meter is 100. So 50 by 100. 0.5 is equal to shear stress, you know, 1.8 divided by, because this is Newton per meter
Yeah.
square. Everything you have converted to Newton.
Meter. Yeah.
So this is G. Okay. So everything you know now here.
Yeah.
Only thing this you don't know is G. So for this material you have to find out for lead what is the G value. You can get it in the table. In your exam they will give it.
They'll give
Even if it is not there, and they will give it. So for lead it is being written as 5.6 GPa. Okay. So for lead it is del x divided by 0.5 is equal to 1.8 divided by 5.6 into 10 to the power 9 GPa. GPa. That means this is also Pascal. Okay. So this is Pascal, this is Pascal. It will cancel out. So knowing everything, you can find out like del x is in meter. Okay. Del x is equal to 1.8 into 0.5. So half of 1.8 is 0.9, right?
Yes.
Divided by 5.6
2.3.
into 10 to the power 9. Okay.
Yeah.
So this is you will get in meter. You can convert it into mm. Okay. So finally you will get the result as 0.16 mm. So del x you will get as 0.16 mm. So you can see that 0.9 by 9. So it will become let us say 9 by 56.
Yeah.
Right? You multiply there by 10. So 9 by 56 is nothing but your 1.6